All right, AP Chemistry, Chapter 4, Types of Chemical Reactions and Solution Stoichiometry. This is going to be Section 4 and 5 of this chapter. Section 4 talks about the types of chemical reactions. Types of reactions. Basically, there are four driving forces for a chemical reaction. Any chemical reaction will fall under these driving forces. It might be a formation of a solid, formation of water or another molecular compound, formation of a gas, or a transfer of electrons. Notice that I have kind of sequestered these three away from this guy, because these three, as we are about to find out, all come under the same broad category of metathesis. And metathesis is nothing more than a fancy term. It's a Greek term meaning exchange, so it is a fancy term for double replacement reactions, which you are all familiar with from first year chemistry. So double replacement reactions. Rxn for short. This guy is his own category. These are oxidation reduction reactions. And they are a transfer of electrons. So while double replacement reactions come under these driving forces, redox are all those other types that you identified first year, like synthesis, decomposition, combustion, and single replacement. And these types of driving forces and these types of reactions, the metathesis and the oxidation reduction, is a huge chapter, and it's really super important because major questions on the AP exam for reactions. So while there are four driving forces, there's actually two broad categories that every reaction can fall under. And the first one is, again, metathesis, which we just discussed, which is also known as double replacement reactions, or DR for short, which you should be able to recognize because the reactants are two compounds and they switch. Their cation will switch with the other cation. There are three categories for double replacement reaction. Precipitate reaction, meaning a solid forms where once there was none. That's when you have two clear colorless solutions and you pour them together and you get a solid forming. Acid-base reaction, which is also known as neutralization. You might form water or a weak acid, which is another molecular compound. Gas-producing reactions is the third subcategory of double replacement reactions. The second category, which we'll tackle at the end of Chapter 4, is the oxidation reduction. This is the one that has a driving force that is a transfer of electrons. And these three guys revolves around ions, the removal of ions from the solution. Section 5, Metathesis Reactions. Metathesis reactions. The ultimate driving force of a metathesis reaction is the removal of one pair of ions from solution. This is basically going to be the story of four ions. Two will be removed from the solution. And 2 will remain in solution as spectator ions. So 2 of the ions will come out of the solution. Those 2 ions will come out and form a product. And when I say come out, I don't mean like they jump out like flying fish. They're removed from the solution. So either in a solid form that will sink to the bottom of the beaker, or an acid-base neutralization reaction where you form water and or a weak electrolyte. Usually that weak electrolyte is acetic acid. The third type of metathesis reaction is a gas producer, and there are 4 gases you have to look for: hydrogen sulfide, carbon dioxide, sulfur dioxide, and ammonia gas. So there's 4 gases to the metathesis reactions that you got to look for. Alright, precipitate reactions. Nice and simple. This is going to be based on solubility rules, which you have a list of, and you have to memorize them. The solubility rules will dictate whether a precipitate forms or not. Acid-base reactions are real simple also. What's not so simple are the gas producers. You actually have to memorize and recognize the gas producers. These reactions will often involve acids and bases, so you have to keep an eyeball open for those. These gas producer reactions will often produce an aqueous substance that is unstable, so it breaks down a second time to form the gas and water. And of the 4 gas producers, this guy right here, the hydrogen sulfide, will be the only one that forms immediately. That when you do the double replacement, he is one of the products. The other 3, you're going to have to recognize the interim substance. And we will do an example at the end of this lesson. Okay, so a couple of examples that you for these gas producing. Again, of the 3 types of metathesis reactions, the gas producers are the ones you really have to be able to recognize when you see them. First example, any sulfite salt plus an acid will form sulfur dioxide gas, water, and a salt. So for example, a sulfite salt, let's pick the nice simple one. Aqueous sodium sulfite and hydrochloric acid. For a double replacement reaction, the sodium will replace the hydrogen, and you will get, of course, sodium chloride. And the hydrogen will replace the sodium, so you will get sulfurous acid. But this breaks down a second time to form water and sulfur dioxide. So you have to recognize this in a metathesis reaction. A little voice inside your head has to say this breaks down again because it is unstable. It breaks down a second time into the water and the gas. Another example, a carbonate plus an acid will pretty much do the same thing. So let's pick potassium carbonate, and let's use nitric acid this time. Again, double replacement reaction because they're 2 compounds. If you predict the product, double replacement reactions, they switch. This cation will replace the hydrogen will replace the potassium, so you get a salt, a soluble salt, solubility rules. and you get carbonic acid. You got to recognize that this breaks down again into your water and your carbon dioxide gas. So again, the issue is recognizing that guy and that guy. Little voice inside your head has to be there to tell you that breaks down a second time. Example number 3, ammonium salt and a strong hydroxide. Okay, so let's see. An ammonium salt, let's pick a soluble ammonium nitrate. You'll notice I am using solubility rules a lot. You have to have those memorized. A strong soluble hydroxide would of course be any of the group 1A or 2A hydroxides, so I'm going to use that. Again, notice double replacement because there's a compound and a compound. The sodium will replace the ammonium will replace the sodium. I will get a salt. Now I'm not balancing these because I just want you to realize there's an interim product. You must recognize it and you must break it down again. If you leave it like this, it is wrong. Little voice inside your head has to tell you that that ammonium hydroxide will break down a second time to form ammonia gas and water. So these 3 must be recognized, and carbon dioxide, sulfur dioxide, and ammonia gas, you just got to memorize them. The 4th one is nice and simple. It just turns up. You don't have to recognize anything. You just do the double replacement reaction and bam, there it is. So let's say, for example, a sodium sulfide reacting with acid. Let's use HCl again. Double replacement reaction, recognizable because it's a compound and a compound. Both reactants are compounds. The sodium will replace the hydrogen will replace the sodium, and you get a salt, which is aqueous, soluble, and you get the 4th and final gas, which is hydrogen sulfide gas. Notice that this guy, you don't have to recognize anything. There he is. End of story. It doesn't break down a second time. He comes right out when you do the double replacement reaction. Alright, keep in mind what strong electrolytes are. Strong electrolytes include strong acids, strong bases, and soluble salts. The soluble salt list is your solubility rules. You must have those memorized. Does not include, so I'm going to give you the list for does not. Weak acids, weak bases, insoluble salts, which are solids, does not include gases, and water. Keep in mind what the definition of strong electrolytes are. Strong electrolytes are substances that dissociate or ionizes in the case of acids 100%. In other words, they break apart 100%. So in terms of sodium chloride versus silver chloride, according to solubility rules, this is soluble and this is not.